Okay, good morning. Okay, so today we're going to try to put the whole system together, like the 2D touchscreen, capacitive. And what that means is that we're going to look at pieces of stuff that we've done in the previous lectures, like understand how actually to model the sensing capacitor, how that thing really works from physical geometry into the model. Then look back into kind of circuits with capacitors that we did so far to figure out how can we actually measure the value of that capacitor, because that will be our unknown. Right? When we put the finger over a pixel, there will be some capacitance that changes, so we want to figure out what that is. And then we're going to introduce another circuit. It's called a comparator, an op-amp, that will make it easier for us to just distinguish between very small current voltage changes. Because sometimes we just want to know whether something happened or not, and this circuit, the comparator, will be able to do that. Based on some small voltage difference, we'll be able to just tell us, hey, there is a huge signal now coming out. Yes, something happened or something didn't happen. Right? And then we're going to later use, in later lectures, this op-amp to do lots more cool things. But here we're just going to use it as a comparator. This is all in Note 17 online as well. One thing I'd like to kind of point out is that we're getting into the second part of Module 2, which means it's kind of like on a roller coaster. We've gone like through this slope, and now we're entering this slope, right before the big excitement. And so I'd urge you to kind of really make sure in the next 2 weeks you keep up the pace with the class and tell your peers, come to lecture, or at least look at the lecture notes, come to homework parties. There's going to be a lot of stuff happening. As you see even on this lecture, we're going to look at equivalent capacitances, do the measurement circuits, introduce an op-amp. Next lecture is negative feedback. We start building bigger and bigger circuits very quickly because we're relying on the fact that we now understand the circuit analysis and superposition and equivalence. So it's just going to snowball from here. So keep yourself braced up and the pace, and you'll enjoy it because you're going to understand kind of the bigger picture. But relate that to your peers as well. The more people come to class and watch the lectures, the easier this is going to be. Okay, so let's dive into it. We'll have a side view, just like we did with the resistive touch. We're just going to kind of look at the geometry, try to understand what's happening here. So I'll have, actually top view and side view. So maybe I just draw the top view first, so it's easier for you to see. So in the top view, I'll have a metal conductor, and then I'll have another metal conductor on top of it. Okay? And they will overlap in this area. I'll call this area A, and we'll call that a pixel. Right. So we're just zooming now into one tiny piece of this whole touch screen, and then later we're going to expand. In that area, we just have two metal wires essentially overlapping. But they're not actually touching, and if you look at the side view, there's going to be this top red conductor, and then that's going kind of into the picture. And then there will be a bottom blue conductor, right? So we're going to call this top, it's metal. And we're going to call this electrode 1, right? And then we're going to call this is bottom. It's also metal. And we're going to call it E2. And so in between these two, there's some insulator with a permittivity epsilon. Right? This is typically, if you look at your phone, it's kind of the screen, it's the glass material. It's various types of glass that's resistant to damage and things like that. And then there is this thickness D, which is the separation of the electrodes. So if you look at this structure, what forms naturally as a circuit element between these two conductors? A capacitor, right? And so this is one plate of the capacitor, and this is another plate. So I'll just sketch it here. Right. And so we can write, this is model without touch. Right. So this is the physical geometry without touch. And then a model, I can just basically draw a capacitor, right, just like we said. It's electrode 1, electrode 2, and some capacitance C0. And what is that capacitance going to be equal? Last lecture we did at the end a little bit of 16A capacitor physics. I think it's enough for you to figure out what this capacitance is. Any suggestions? Over? Oh, okay. So the suggestion was this epsilon for the insulator times this area over distance d. Yeah. I think that's nominally what happens. There are some other capacitances from kind of the side of the conductor down. Those are called fringe. But we're going to ignore those for now. They're typical. If the conductor is thin and wide, then they're kind of negligible. But we'll see in some other cases they're not going to be. So this is basically a case with no finger, right? Just the screen and so on. But now if we want to add the finger, we don't really want to directly add the finger to this picture touching this electrode 1, because we don't really want to get zapped or anything. We don't want to have anything with voltages or currents on the phone. We want to be isolated from that with a nice, like, smooth surface. So what we're actually going to do is add another insulator. So we're going to add an insulator. And so our picture is now going to look something like this. So here is the extra insulator. Here is the metal, electrode E1. So let's just label it E1. Here is the rest of the stack, just like above, right? So this is E2. Okay, and now we still have C0 here. But now I'm going to add a finger, and I'm going to add it's going to look really ginormous. Right? And actually I've like shrunk the finger. In reality, you have, couple thousand by couple thousand pixels on your phone. On larger screens, even more. So when you touch with your pen that you're writing on your tablet or on the phone, the tip of the pen already is covering several pixels. Not to mention when you press with your finger. Your finger, there's many, many pixels that actually see your finger. So I've kind of shrunk the finger in this picture to be kind of a lot smaller with respect to the pixel than it really is. So really the finger acts as this giant plate, right, on top. Okay. Given this, what happens now with capacitances? What can we treat our finger as? What do you think? What type of material? A conductor, right? We're full of which substance? Water, like salty water, right? And so we conduct current pretty well. You don't want to conduct a lot of it. You get a heart attack. But we can conduct current pretty well. So finger we can just treat it, the first order approximation, just as a metal plate. It's a conductor, right? So now we have a system of 3 electrodes. Electrode 1, electrode 2, and I'm just going to label this electrode F for finger, right? And, we can label these distances, distance 1, distance 2, of all these electrodes. That would be if I tried to kind of calculate really what all these capacitances are. But let's see what happens now. If I add this electrode, what other capacitances do I have in my system? Here, when we added E1 and E2, we had C0. Now we have another electrode. So what are all the other capacitances that get formed? Any ideas? Yes? Okay. So one suggestion was between E1 and F. So I'm just going to draw it here with green. CFE1. Okay? So, any other? Anything else? Yes?
Is there one between the finger and the bottom plate?
Yep. So, there is a capacitance between the finger and the bottom plate. And so I'm going to call this CFE2 left. And of course, there is another one here. And we can call that one, okay, it's getting messy, CFE2 right. Okay. Oh my God, so like 4 capacitors. What are we going to do? So, let's create a model. This is pretty messy physical picture, but we can try to create a very simple model out of it, which is kind of always the goal. So let's do a model with touch. Right, so this above was modeled without touch. It was just a single capacitor. And here, usually when you get into these kinds of problems, it really helps to label the nodes. And then you can easily see which elements are connected between each nodes and see if you recognize some sort of a pattern, right? So let's see which nodes do we have here. We have node F, that's our finger. We have node E1. And then we have node E2. That's the bottom electrode. And so now, let's just go now between the nodes and see what are the elements that exist. What is the element between node F and node E1? Yeah, CFE1. That's this green capacitor. So I'll just draw it as it was drawn over there, right? So this was CFE1. Between E1 and E2. That one is easy. C0, right? Okay. C0. And now, between F and E2, how many elements do I have between F and E2? Between here and here? 2, right? And, okay, so let me draw both of them. I'll draw them all on one side. So, but hopefully that's not confusing. So I'll just draw them here. And then there's another one. So what I'm interested in is figuring out what is the equivalent capacitance between nodes E1 and E2. Because I cannot reach node F. My phone only has access to electrodes E1 and E2. So node F is something that the phone cannot see. That's the user, right? So the phone circuits can only apply apply some measurement only on electrodes E1 and E2. So that's what I'm interested in. Here, in no touch situation, I had C0 as a capacitor between E1 and E2. So that was some value that I could access and measure. I want the same thing here. So why don't you take a minute and talk to each other and see if you can figure out what is the equivalent capacitance between E1 and E2 in this model. Think in terms of the patterns that we did last time. Capacitors in parallel, capacitors in series. See if you can decompose this. Okay, any ideas? Anyone in the back? Yes? Can you speak up? Okay, so let's do one thing at a time. So you're saying C0, okay. And then you're saying parallel operator with what? CFE1, and then? And what about these two? I mean, they're still part of this circuit, right? So if I was applying I test, dV test, dt, some current would go there, right? So somehow I need to see them in this equation. Okay, yeah. Just add them. Okay, but you're saying C0 is in parallel operator with this one, right? Okay, how many people share that opinion? How many don't share that opinion? Okay, can you say why? Okay, so you're saying it looks actually like C0 is in parallel with whatever is up here, right? It's not just CFE1, it's whatever this is too, right? So but it's kind of hard to see because I didn't draw it, so it's easy to see, right? But okay, maybe let's take one step at a time, because this looks really messy. What's the deal with these two? Can I combine them into something that's easy? Someone? Yes. Yeah, so let's just do that because it's easy, right? So I'll just do that. So CFE2 left plus CFE2 right. I know this is an equivalent capacitance, right? Okay, so now these two become one capacitor. And then that capacitor is in what relationship to this capacitor over here? In series. So, okay, how do I then come up with an equivalent capacitance of that plus this? Parallel operator, right? So I'll do a parallel operator with CFE1. And then when I look at all of that as one capacitor, between which two nodes is that capacitor? E1 and E2. So what's the relationship to C0? And so how do I combine this with this? Yeah, so I just add a plus sign. Okay? So let's actually go through these steps because I'm pretty sure there are a bunch of... Should I go and break this down for people? Yes, okay. So let's do that. This is not an easy one, so don't worry if you're not really seeing it here. So let me draw this in a slightly different way so you can actually see more what's actually going on. Okay, does this make sense? So here's the original one, right? So I'm just tracing, so between E1 and E2 there's C0. And then I just moved this one on this side just so I can see things more easily, right? But CFE1 is still between E1 and F, so nothing really changed, right? Yes? I could move things around, but notice what I'm trying to do here is move things so things are between nodes E1 and E2. I can more clearly see what is exactly between E1 and E2. Does that make sense? In fact, maybe one thing to do is let's just go from the one that was the original one. Maybe the moving around is confusing. But I just wanted to say here, then it's easy because what you go and just say, these two are in parallel, so what I really have is CFE1, and then this one is CFE2 equals CFE2L plus CFE2 right, and then I have C0. This is node E1. This whole thing is node E1. This whole thing is node E2, right? And then these two, then this is equivalent to this capacitor here is CFE1 parallel operator CFE2. And then that's with C0. these nodes are still E1, E2, right? And then that finally is just one capacitor, which is C0 plus CF E1 parallel CF E2. Right? Does that make sense? That's kind of easy when I redraw it like this, but you can also just go from this drawing that we did previously. So let's just do that if people are confused still. So this is F. There is CF E1, E1, C0. And these are CF E2 left, CF E2 right. So I'll first see that these two are in parallel. So I'll combine those two. Right? So this is CF E2L plus CF E2R. And so now, so that let's call that again CF E2. So I'll just combine those two into CF E2. Again, okay, this is electrode E2. So that is still between electrode F and electrode E2. And then I have still these two capacitors between E1 and E2, so C0, CF, E1. That hasn't changed. That's this branch over here. Now, I go around this loop between E1 through F and to E2. That's a series connection, right? I'm just going up. E1F, F, E2. Those are two capacitors. And so I can mark those as a parallel operator. Right? So that capacitor is now connected between E1 and E2. And I still have C0. So the equivalence of that is a single capacitor, which is C0 plus CF E1 parallel CF E2. Right. So, essentially, you can go either way. Either try to see in your existing circuit what are the smallest patterns, subblocks that you recognize what they are, and start simplifying from there. And then hopefully things will become clearer. So it's a kind of cascaded equivalence. Or try to redraw your circuit so it is more clear. But when you're redrawing, just make sure that it's like a graph. Your nodes, vertices are your nodes, and your elements are the branches in the graph. And make sure that you always obey. Yeah, let's...
So if we went from E1 to like E2 and then E2, these are also in parallel with
If you go from E1 to E2, you see C0.
No, the one below it.
This one.
From E1 to E2 and then to F. These are also in series. But does that mean that's what I'm confused about? Why do you go up and like not down?
Okay, so let's go down between E1 and E2. What do you see?
C0.
Okay, that's this. And then, so that's one element between E1 and E2. What's the other element between E1 and E2? It's this whole branch, right? And that's this, right? So just trace the branches and treat the nodes as graphs, as vertices on the graph. That's it. Yes, there was a question there. You had a question? Okay, so you're saying you're confused how CFE1 is in series with CFE2. Think about how we define the series. The elements are in series if the same current flows through them, right? So if we go from E1 up, there is a single branch. There's nothing else going on, right? So one single current must flow through all of them, right? Yeah. Yes.
So doesn't it depend on
Does it depend? Let me interpret that question. All of these equivalences depend on between which two nodes you're looking. Right? I think that's kind of what you're asking, right? Yeah. So this is exactly why I was saying we're interested in equivalence between E1 and E2. Because those are the electrodes that we have access to. The finger is the user. It's isolated by a dielectric. The circuit cannot even touch the user, right? So I'm never interested in this node F. That's why through these equivalences, you see in the end, I don't even see node F, right? It disappeared. But I don't care about it. I only care about the value of the capacitance between the electrodes that I can access, right? And you're right. If for some reason I was interested to know what is the equivalent capacitor between nodes F and E1, that will be some other value, right? And we can go and write it out for practice, but it's a different value, right? Yes?
So right now you're saying you're going from E1 up and then down. What prevents you from doing the other way around, going from E1 down and up? So then like your operator down there, instead of being CF E1 parallel to CF E2 and C0 parallel to CF E2.
Oh, okay. So you're saying, why don't I go this way? Well, keep in mind, I'm still going from a node to a node. So just like we did over there, going down from E1 to E2, what do I see? Okay, so that's my element here. So I'm now in E2. Going this way, what do I see? Well, I don't just see CFE2. I see CFE2, and then to come back to E1, I see CFE1, right? So just keep up with me. From E2, I go this way. I see CFE2. To come back to E1, I can't just jump here. I need to go back through CFE1. So then I just visited both CFE2 and CFE1 on the same path. Right? So that's a whole branch. Well, that needs to be represented with some capacitance. That's this capacitance, CFE2, CFE1 parallel operator CFE2. Right, so what we did, we went from E1 down to E2, that's C0. Then we went from E2 to E1, and that's this capacitor. Does that make sense?
I still don't understand why that's not reflected when you go up and down. So if you go from like E1 to F, you see CFE1, and then when you go from F all the way back to C1, don't you see CFE2 and C0 as a single branch? Why can't you treat those?
Okay, just think about it this way. I'm only interested what's between E1 and E2. Okay? How many branches exist between E1 and E2? 2 branches. What is in the first branch? C0. What is in the second branch? A series connection of these two. That's it. Right? So, really, if you're confused, just don't even draw things like this. Draw a graph. Draw the nodes and see what are all the branches between the nodes. Sometimes you'll see 2 branches between the nodes. Well, those are in parallel. Does it make sense? Like what I'm trying to say is like, I can just draw it like this. E1, E2, F. This is a graph. So let's see what's going on. Well, I have C0 between E1 and E2. I have CFE1 here, and I have here CFE2. If I'm only interested in this node and this node, I see 2 branches. One branch is this, another one is that. And those 2 branches are in parallel. Right? And that's all there is to it. So if you're confused about these wires and stuff, just draw the circuit as a graph, because it is a graph. And then hopefully parallel series will come more naturally. Any other questions? This is tricky stuff, so it's really important to understand how to view these schematics. Yes?
So why is C0 not in series with CFE1 parallel CFE2?
Okay, so when you say something's in series or parallel, you have to also think about between which nodes are you looking for the equivalence, right? If I was looking for the equivalence between nodes F and E1, right, then there are two branches there. One branch would be CF-E1, another branch would be this whole branch. So then C0 would be in series with CF-E2 on that branch. But I'm not doing that. I'm looking at equivalence between E1 and E2. So between these two nodes, there's two branches. One branch is C0, another branch is this branch. And C0 is not in that branch. Does that make sense? So the equivalence always shows up between some two nodes, and then you look at what are all the branches between these two nodes in the graph. The equivalence is not the same regardless of which two nodes you pick in the circuit, right? Yes?
Probably we had just assumed that between node U1 and U2 there are some external circuit, and then the curve that flows into U1, we can clearly see that it leads to like two branches.
Yes, so the comment here was, really what's happening is this, right? We want to attach something to these two electrodes, E1 and E2. So hopefully these two wires don't confuse people even more, right? Now there is some element that I want to model, right? Some equivalent. I want this to be just some equivalent capacitor CEQ between E1 and E2. And here is E1, here is E2. I want to attach that to some other circuit. And in a moment we'll do exactly just that, right? So you are interested between these two nodes. Okay, so bottom line here is that C equivalent in the touch condition, C equivalent between E1 and E2 equals to C0 plus some delta C. Right? That delta C is essentially this CF E1 in parallel with CF E2. And it's some quantity that's always greater than 0. Capacitance is always greater than 0. Right? What this means is when my finger touches, the overall capacitance between nodes E1 and E2 increases. And that represents information. If I could somehow measure the value of the capacitance, I would know that the finger is there, and then I'm done. Right? Because my whole purpose was to sense the presence of the finger. Then I know, we'll see later at which coordinate it is, etc. Right? Okay. So, let's just really quickly expand this to a 2D view. Before we figure out how to actually go and measure this capacitance, but just to show you how things work. In 2D, we again have the same thing. We have vertical and horizontal wires. And each one of these cross-sections will be a pixel. Right, so let's say this upper left pixel would be x1, y1. Coordinate, right, etc. And since we have a model for what's happening on a single pixel, my circuitry will just go one pixel at a time between coordinates. So we used to call this, let's say, E1, and this we called E2, right, in the single pixel example. But now I'm just going to be changing. My x1 will be E1, my y1 will be E2, and then I'm going to change. My x2 will be E1, my y1 will still be E2. So I'm just going to go have a circuit that interrogates each pixel separately. Right? And I can do that because I have this 2D grid. Right? If I put, let's say, some measurement circuit between y1 and x1, I will measure this pixel. If I put between x2 and y1, I will measure that pixel. x1 and y2, I will measure this pixel, and so on. I can measure every single pixel in the whole screen. And that's indeed what the circuitry does in your phone. It's just super fast. It does this at, nanosecond type levels, and your finger moves way, way slower. So your phone can interrogate millions of pixels by the time you don't even move your finger, right? So it can sense the movement of the pen, of the finger, of things like that. Okay, the key question becomes now, how do we measure the capacitance? What circuits do we use to do that? Right. So, maybe there's some ideas here. Anyone has any idea? Maybe based on something we did last lecture. How do we measure stuff in general in circuits? We have some physical quantity. To which quantities do we want to convert it? In this case, it's a capacitance. It could be distance. That's what we did with resistive touchscreen. We had distance. We converted that somehow to a change in resistance. And then we converted that change in resistance into what quantity? Voltage. Here, we have, again, distance, which is the location of our pixel. We converted that already to a change in capacitance. Great. We're getting closer, warmer. Now, what's the quantity we want to convert this to? Something our circuit can understand. Voltage or current, right? Those are the two things our circuits can measure, process, and things like that. Okay, so we want to convert it to voltage. So essentially, want to convert capacitance value to voltage. Yeah, that's our task. So let's do the first thing. We did kind of a circuit earlier, last lecture, that was kind of doing that relationship, right? Anyone remember? Maybe? We had a capacitor and we added a single element, some type of source, that was able to convert the capacitance to voltage. Yes? When we added a voltage source, a voltage source applies a fixed voltage across a capacitor. It doesn't really give me a new value, right? I want to apply something so that the voltage contains the capacitance information. Which one? Current source, yes. Okay, so let's do that. Okay? Let's say I apply the current, and then there's a capacitor here. This capacitor is this pixel capacitor, right? So I'm just going to call it C equivalent. And I want to measure a voltage between these two electrodes, right? So can anyone tell me what's the equation for that voltage? This is a constant current source. So we derived this last lecture. I put time here, so this should be a hint. Constantly charging this capacitor with a constant current. So, and the capacitor current was a derivative of voltage, right? So that means that the voltage has a constant slope. Yes? Okay. Yeah. So this is the equation, right? We have a constant slope that's proportional to current, inversely proportional to capacitance, times the time, plus Vc of 0. Right? So that's some initial voltage. And if we go and draw kind of the Vc versus time, there's some Vc of 0, and there's going to be some slope here, right? Is over C equivalent. Now notice here, the slope has capacitor info. Right? So if I can measure the slope of the voltage, then I'm done. I know if this capacitor is changing, the slope will be changing. Right? As I'm pressing the finger, the slope of integration will be changing. Now, Vc of t here grows indefinitely. Right? So that's really a problem for practical implementation. Right? Grows indefinitely, it's just really going to, in practice, blow up. Something's going to blow up, either the current source or the capacitor itself. We talked about it in the last lecture. That's why the lightning happens, right? The voltage increases. At some point, you hit the critical field, and you punch through the insulator. Okay, so in general, for constant I source, we can rewrite this equation from, let's say, sometime t0 to t. This will be Vc of t equals Is over C equivalent times t minus t0 plus Vc of t0. People see that this is just the integration thing, right? I can always start the integration from some t0 and move on. As long as the current is constant, I just get basically this, right? Okay, so this I'm going to use to make a second attempt. So let's call this attempt number 2. Okay? So I'm going to make the current source periodic to limit Vc of t. What do I mean by this? Well, we know that the slope of the voltage is related to the current, right? So how do I reverse the slope? So if I have positive flow of current, the slope goes up like this. How do I reverse the slope to go down like this? What do I need to do with the current? Yes? Yeah, I need to flip the sign of the current. So if I apply a periodic current source that for some time is positive, for some time is negative, I can actually make kind of a sawtooth type waveform, triangular waveform. So this is Is. Okay, so it's now Is as a function of time. And I'm just going to draw it like this. This is now our current source. It's the same capacitor. So the circuit looks the same. I just changed how this source looks like, right? So let me maybe draw a bigger diagram here. What's actually going on? So Is of t, I'm going to label it so it's I1 here. So that's its time. So this is t over 2, t, 2t, etc. Right? And so this current is minus I1. So just imagine I have a source like this. You'll see in the lab we can actually, and later we'll actually make this source out of voltage sources and some op amps and stuff like that. But for now, let's just assume I have it. Right? If I had a source like this, life is great, because I will be able to get during this period of time, I'm charging up the VC, so the voltage is going up, and then during this period of time, the voltage is going down. So let's derive that real quick. So for time t between 0 and t over 2. So we're just going to use essentially this equation here that I already had. Right? So we have Is of t during this time is I1, right? Equals I1. So I'm just charging up the capacitor, so it's Vc of t is just what we derived already. It's I1 over C equivalent times t plus Vc of 0. And I'll just tell you, let's assume that this is 0 for now, right? So let's draw that waveform. So we have Vc of t here, and that's going to go up to some point here. And that point is going to be I1 over C equivalent times t over 2. Right? Because when this one hits t over 2, I have I1 C equivalent times t over 2. Right? That's the maximum voltage I'm going to get. Okay? Then what happens? When t is between t over 2 and t, I now change the sign of the current. So the current, Is of t, is now equal to minus I1. Oops. Yep. So current is now equal to minus I1. Right. So let's just plug it into this equation. Then Vc of t is equal to, at that point, the current is minus I1 over C equivalent times t minus, and our t0 is t over 2, because we're starting from t over 2, plus our starting voltage is what? Vc of what time? T over 2, right? Do we know what that is? Well, Vc of t over 2, I know from the first equation, right? What is that? We just labeled it on the picture. I just plug in time t over 2 here, right? So it's I1 over C equivalent times t over 2. Okay, so I can then say this Vc of t equals minus I1 C equivalent times t minus t over 2 plus I1 C equivalent t over 2. Okay, what is C Vc of t? What is Vc of t when you plug t into this equation? 0. Right? So if you look at this equation, the slope is now negative, right? Because it's minus I1 C equivalent t. And we know the starting point, it's here, and we know the end point, it's 0. So the line looks like that. Now, the new period begins, t. We're at 0, which is the same as the starting point. How is this waveform going to look like? Going up or down? Up. Right? It's going to be the same. Again, I hit I1 over C equivalent times t over 2, and I come down to here, right? And then I come back up, and then down, etc. Notice, here I didn't assume that C equivalent is changing. I just said for some fixed C equivalent, this is what happens, right? Now notice that this peak voltage, so let's call it here maximum of Vc of t equals I1 over C equivalent times T over 2. This maximum voltage contains actually the information about capacitance. Right? It's no longer just in the slope. It's in the actual value of that peak right here. Does that make sense? So previously, when we were just integrating with a constant source, our value of the capacitor was in the slope. When we applied the periodic one, now, because we've limited the time that we're integrating, now that value, the peak value of the voltage, has the capacitor information. If the capacitor is bigger, where does this value go? Increase or decrease? What do you think? If you look at this, if the capacitance increases, does this value increase or decrease? Someone? Decrease, right? If the capacitor decreases, the value increases. That's information. I can use that. If we go back to touch, we know that when the finger touches, what happens with the capacitance? Increases or decreases? Increases, right? So, if now the finger touches and I'm measuring, where is this maximum voltage going to go? Up or down? I have more capacitance when the finger touches. So where is this voltage going? Up or down? Yeah, down, right? So let's draw that. Okay? Okay. So before we do that, actually, let's just do it. So let's do this is Vc of t. And this is time. So let's say at 0 we start, and I'm just going to be drawing the Vc value. Assume there is some periodic current source that we applied, right? So it's going to go up to our I1 over C0 times T over 2. Going to come down, come back up, come down. These are the same values. Now, if this period we can call no touch. Right. If the touch happens, I'm going to get a smaller value. So this is T, 2T, 3T. This value is going to be I1 over C0 plus delta C times T over 2. You see that? So there is some difference, delta voltage, between these two. Remember, our C equivalent was equal to C0, no touch, C0 plus delta C, touch. Right? So this small change in voltage max, right, is I1 over C0 minus I1 over C0 plus delta C times T over 2. Or you can even take out I1, doesn't really matter. It's a small change because delta C is typically small. You'll see in the lab when you add a finger, it's not going to add that much capacitance. Right? Okay. Now the question is, how do we get a bigger change in voltage? Right. So that's kind of the next part. We somehow need to amplify this change into something that follow-on circuits can more easily detect. Right. Before we do that, I just want to go back and clarify one little point, and that was that I sort of assumed here that VC of 0 was equal to 0, right? I need to somehow guarantee that at the beginning of the measurement, right? And so the way to do that is I'm going to introduce another element that exists in circuits, and that's a switch. And a switch acts as an open circuit when switch is off or open, or acts as a wire when switch is on or closed. And there is some control signal here that will tell the switch to turn on or off. It's like when you're pushing the button to turn on the light, right? Or your phone. There's some switch in there. So for now, this is just an ideal switch. Don't worry what device actually does that. But if we have something like this in our circuit, we can add that element. Right, this is our periodic source. We can add that element, and at whichever time we want, so we would keep the switch on. When we keep the switch on, basically VC of t is equal to 0, right? Because it's just a wire across. So all of this current is going, instead of into the capacitor, it's going around through this wire. And VC of t is 0. Voltage across the capacitor is 0. Across the source is 0. Nothing really happens. When we open the switch, that's when the action starts happening. That's when the source starts charging C equivalent. So we can always know when this time happens. Right? That's just a convenience, basically, to be able to control when the measurements happen. Does that make sense? Okay. Okay. We're going to jump now to the op-amps to answer this question. How do we get a bigger change in voltage? Are there any questions about this charging of a capacitor, things like that? Yes? Mm-hmm. So you're worried about this situation. IS? It's a current source. It's going to be good, right? Because in this case, this is just a wire, right? So the voltage across a wire is 0. We know that if there's a constant voltage across a capacitor, which in this case is 0, the current through the capacitor is 0. So all the current is really flowing through the wire, nothing happens. It's cool. Okay, yeah, good question. Any other questions? Everyone's okay with this charging? You'll see this in the lab. In fact, you're going to touch 3A is all about rederiving this so you get more comfortable. Does it make sense for now? Okay, good. So let's introduce the new element. And that's going to be our op-amp, operational amplifier. So this can be used as a comparator. And that's what we're going to use first. And this really compares two potentials and determines which one is larger. Larger. All right. So if you just you don't want to deal with what exactly those values are. You just want to know, hey, is this larger than this? This is the element for you. Right? And usually, yes? Comparator. Yeah, sorry, my handwriting is not the best. Okay, so let's just do a symbol for this first. Just like we introduced stuff previously. This one is a little bit more complex, lots more stuff to draw. So bear with me. Okay? So we're going to label this input terminal as plus, so there's going to be some potential U plus here, some potential U minus here. The output will be U out. And I'll put this thing here. Who remembers what this is? There's some squiggly. Yes. That's ground, or I like to call it a reference node. Every circuit has to have a reference node. That was our 7-step procedure, right? This is what we were labeling 0, right? Or you can call it ground. Right? And remember, I measured voltages, all the voltages with respect to that ground, right? All the potentials were expressed as really voltages with respect to that ground. So if I wanted to say output voltage, I'd really measure it with respect to ground. Right? This element is a little bit different than the other elements. It kind of needs the supplies to work, right? So I'm just going to add here the two other terminals, and I'm just going to label them. This is kind of traditional labeling. So VDD and VSS. Okay, so that's really just the symbol. And we're going to see how later how to wire it up in circuits. But for now, it's just a symbol. And let's look at what the model for this is. Right. So how it works is these two terminals, U plus and U minus, they just basically give you this control voltage, VD. VD voltage is just a difference of these two potentials, right? It's U plus minus U minus, just because of this plus and minus. And then what I connect to the output are two voltage-controlled voltage sources. Right, the first one I'm going to call VDD plus VSS over 2. This node is VSS. I'm going to add another one of these. This one will be A times VD. Remember, VD is this over here. And then I have my U out. Of course, I want to have this ground present in the circuit so that the difference between the ground and U out is V out. Okay, so whenever you see this symbol in the circuit, you can always represent it with this model. so that you can analyze the whole circuit. What is in this model? What is this element over here? One of the simplest ones that we've done. Anyone in the back? This element over here. Yes? Okay, so this is a wire, but this element, what is it? Between U plus and U minus. Open circuit, right? Open circuit. What is this element? This diamond thingy. Voltage-controlled voltage source. This source is controlled by the values of VDD and VSS. Those are these values on these terminals. Right? In fact, I'm just drawing one here. The other one I'm not really drawing in this diagram. What really is happening is that I also have some battery, VDD, between, again, a ground, same ground, and I'm calling this terminal VDD. And I also have a battery, VSS, and I'm calling this terminal VSS. So these are the same terminals. This VDD is this voltage provided by this battery. Right? So this is a voltage-controlled voltage source. What is this one? This other diamond here. Looks the same. Must be the same element, right? It's also a voltage-controlled voltage source, but it's controlled by a different voltage. Which voltage? VD. That's this open circuit voltage at the input. And then there's this A. A is just a constant. It's a gain. We call it a gain factor, right? So in ideal op-amp, A goes to infinity. Right? In a practical op-amp, A is actually really large. It's like 10,000, 100,000, a million. That's kind of the value that you should think about. Okay? So let's just write up mathematically what this, let's just solve this circuit real quick, right? So V out equals what? I'm looking at V out between this node and this node, right? So maybe I give you 1 minute to kind of figure out what V out is. Yes? Okay, great question. Great question. Are there supposed to be any wires? This looks weird. Okay, I agree. Okay, so let's just sidebar to this circuit that should be familiar to everyone. Familiar? Okay. I can redraw that circuit as something like this. Does that make sense? There's no wire here. I can draw it also. Or let's draw it first. And I just replace this 0 with this symbol over here. Because that's the same node, I will now freely go, just for the sake of clutter, removing clutter in my schematics, I will also draw it like this. So all of these are equivalent. This symbol just means anywhere I draw it, it's the same node. There is actually a wire connecting all this. In fact, in your own circuit, that wire will be called ground. Right? If you don't connect all of these points in your actual circuit, it's not going to work. Right? But the way I'm going to draw schematics, I really don't want to draw wires like all the way between all of these. It's going to be very messy. Right? When you start drawing bigger schematics, it's just going to be very messy. So we're just going to draw these little squigglies and assume these are all connected. when you're doing your board layout, you got to be very pedantic about connecting all these to some common potential, right? This reference node. Does that make sense? Okay. That's a great question. So, let's go back here. 1 minute. We're going from VSS. VSS, remember, is this. So it has a common node. This has a common node. How do we go from here to here, from here all the way up to answer what V out is? Maybe talk to your neighbors for 1 minute. Let's see if you can figure it out. There's only one rule you need to know, one circuit rule that we learned to apply to here. Okay, any ideas? Yes. Yeah, we can do that, definitely. So, do you know the answer? Okay, so we have, sorry, this was, let me see, this is VDD minus VSS. Just a little correction. So, okay, let's go from this node over here. That's a common node, right? So we go VSS up. Now we're here. Another voltage source up, that's VDD. VDD minus VSS over 2. Plus another voltage source up. That's A times VD. And we're at V out. At U out, right? And V out is U out minus the same source where we came from. Right? So this is really just KVL. Does it make sense? We just went in the loop. From ground up to VSS, up this way and down this way. Banzai? Heads exploding? Almost? Okay, it's just a KVL, so think a little bit about it. Now, this is only when this voltage, this whole voltage, when this whole voltage, let's call it VSS, in this case, this will end up being VSS plus VDD over 2 plus AVD, is smaller than VDD or greater or equal to VSS. Okay? The reason is that this op-amp can only supply the output voltage that's between these two supplies. It cannot go above that. So I need somehow to limit the behavior. And then there's going to be VDD here and VSS here. So let's call this value V star. So when V star is greater than VDD, it will be just VDD. And when V star is smaller than VSS, it will be just VSS. Yes? Here? Here? Well, I just added VSS to minus VSS over 2, so it became VSS over 2, right? Yeah. This whole expression is equal to V star, right? Okay? This makes sense? Yeah. Next lecture, we're going to draw kind of how this really looks like in the whole circuit. But just remember that the op-amp can only give you the voltage between the two supplies and not more. Thanks.